If you force two protons together, they violently repel each other. They both carry a positive electrical charge, and like charges push apart. According to the classical rules of electromagnetism, specifically the Coulomb force, packing dozens of these positively charged protons into the microscopic core of an atom should cause the entire structure to instantly detonate. Yet the matter all around us, from the screen you're looking at to the cells in your body, holds together completely stable. The physical architecture of matter relies on a precise hierarchy of subatomic forces that successfully override classical electromagnetism. To understand how the universe actually holds its shape, we have to quantify the exact mathematical tension between these conflicting physical forces. We start by shifting our scale downward to the physical bedrock of the nucleus, protons and neutrons, collectively known as nucleons. For a long time, these were thought to be the bottom floor of physics. But nucleons are composite structures. If you break a nucleon open, you find quarks. These true primary building blocks are tightly trapped inside every proton and neutron. Inside that confined space, they engage in extreme mechanical interactions, constantly exchanging particles, generating intense force fields that bind them together. This internal binding mechanism is so powerful that a small fraction of the force leaks out beyond the boundary of the nucleon itself, reaching out to interact with neighboring particles. The macroscopic stability of the universe is dependent on these microscopic force interactions confined within the radius of a single nucleon. Inside the nucleus, two main forces are engaged in a mechanical struggle. The first is the destabilizing actor, the Coulomb force, actively pushing protons apart. The Coulomb force has an infinite range. Every single proton in a nucleus is simultaneously repelling every other proton, regardless of their position. The counterforce holding them together comes from that leaked quark energy. This forms the residual strong nuclear force. Unlike the Coulomb force, which only cares about electrical charge, this strong force binds all nucleons, protons to protons, neutrons to neutrons, and protons to neutrons, with equal strength. This graph maps force strength against distance. Looking at the blue strong force curve, we see a massive limitation. It only operates at extremely tight ranges. If two protons drift apart beyond roughly 3 femtometers, the attractive pull of the strong force drops to 0. At that point, the repulsive Coulomb force dominates. Therefore, the physical size and stability of any atomic nucleus is strictly limited by the absolute 3 femtometer reach of the strong nuclear force. We can set up a quantitative thought experiment to calculate the exact mass of isolated protons and neutrons and compare that to the mass of a fully assembled nucleus. Classical mechanics assumes mass is additive. The whole should equal the exact sum of its parts. But physical data presents an anomaly. A fully assembled nucleus weighs strictly less than its constituent protons and neutrons. We define this as the mass defect. The architectural rules of subatomic matter dictate that physical mass is not conserved when particles bind together under the strong force. This creates an immediate physics problem. Where exactly did that missing mass go? To solve it, we apply Albert Einstein's mass-energy equivalence principle, E equals mc squared. This formula proves the mass was not destroyed. Instead, during the actual binding process, that amount of missing mass was converted directly into energy. We call this resulting output nuclear binding energy. It is the precise amount of mechanical energy required to completely disassemble a whole nucleus back into its separate nucleons. A stable atomic nucleus owes its physical integrity to the massive energy debt required to tear its architecture apart. Because the interplay between the strong force and the Coulomb force is so delicate, altering the exact ratio of protons to neutrons shifts the total binding energy of a nucleus. This introduces isotopes, variations of an element with the same number of protons but different numbers of neutrons. We also see isotones, holding the neutron count steady while varying protons, and isobars, using different particle combinations to reach the same atomic mass. You might assume you could just keep adding neutrons to increase the strong force and build infinitely heavier isotopes, but that strategy eventually fails. As a nucleus grows from the addition of neutrons, the physical distance between its outermost particles increases. Eventually, the outermost protons exceed the 3 femtometer range of the strong force, leaving the repulsive Coulomb force as the dominant actor. There is a hard, calculable limit to how large an atomic architecture can grow. Once a nucleus exceeds that threshold, those internal repulsive forces inevitably rip it apart from the inside out, triggering explosive radioactive decay. We can evaluate the outcome of all these force mechanics through a single unifying metric: binding energy per nucleon. This graph maps binding energy per nucleon against atomic mass. The higher the average binding energy for each individual nucleon, the more stable the element is. Notice the absolute peak. Elements at this apex, specifically iron 56, represent the most structurally sound matter, reaching maximum efficiency. The physical evolution of matter, from stellar nucleosynthesis inside dying stars to the dense metal cores of planets, is driven by an underlying tendency to seek this exact mathematical peak of force equilibrium. Once we understand the rules of stable matter, we can begin the active manipulation of unstable matter through nuclear reactions. By intentionally breaking apart heavy, unstable isotopes, or by fusing extremely light ones together, engineers can move the matter up that binding energy curve and harvest a fraction of that massive energy debt. This theoretical energy release is the physical foundation for massive-scale industrial power generation. Precision understanding of isotopes and their specific decay rates allows us to map the human body using advanced diagnostic medical technology. The Standard Model provides the mechanical blueprints for the atomic void, serving as the foundational discipline for modern high-energy engineering.